The Second World War witnessed an unprecedented revolution in military communications, from compact handheld transceivers that soldiers carried into the chaos of battle to massive strategic installations that coordinate entire armies across continents. This video breaks down every important radio system deployed across 6 years of devastating global conflict. These devices form the invisible backbone of modern warfare, enabling the coordination of air, land, and sea operations that determine the fate of nations. Without radio, the combined arms tactics that define this war would have been impossible, and the outcome of countless battles hinged on the ability of commanders to communicate with their forces in real time. Let us begin with infantry radios, the portable devices that connected foot soldiers to command structures across every battlefield of the war. The SCR-300 was the standard American portable radio that revolutionized infantry communications during the war. Motorola, then known as the Galvin Manufacturing Company, received a contract from the War Department in 1940 to develop a portable battery-powered voice radio for field use by infantry units. The project engineering team included Daniel E. Noble, who conceived the design using frequency modulation, and Henrik Magnuski, who served as the principal RF engineer. This backpack-mounted unit earned the nickname walkie-talkie, becoming the first radio to receive that designation. The SCR-300 operated in the 40 to 48 MHz frequency range and was channelized for easy tuning across 41 channels. The radio was an 18-tube battery-operated VHF transceiver that used a frequency modulation transmitter section and a double superheterodyne receiver. Weighing approximately 38 pounds with batteries, it allowed a single soldier to carry reliable communications into combat. The final acceptance tests took place at Fort Knox, Kentucky in spring 1942. Motorola produced nearly 50,000 SCR-300 units during the course of the war. The radio first saw action in the Pacific Theater beginning at New Georgia in August 1943. Colonel Ankenbrandt informed General Meade that they were exactly what was needed for frontline communications in that theater. Range reached approximately 3 miles, depending on terrain and antenna configuration. The SCR-300 marked the beginning of the transition of combat net radio from amplitude modulation to frequency modulation, providing clearer communications that resisted interference far better than earlier systems. The SCR-536 holds the distinction of being the first true handheld self-contained transceiver to see widespread military use. Developed in 1940 by a team led by Don Mitchell, chief engineer for Galvin Manufacturing, this compact device was originally designated a handy-talkie to distinguish it from the larger backpack-mounted SCR-300. By July 1941, it was in mass production. The SCR-536 incorporated 5 vacuum tubes in a waterproof case and weighed only 5 pounds with batteries. The operator simply pulled out or pushed in the telescoping antenna on top, which operated an internal switch to turn the radio on or off. Power came from a 1.5-volt dry battery for the filament supply and a 103.5-volt battery for plate supply. Battery life was approximately 1 day of normal use. The unit operated in amplitude modulation voice mode between 3.5 and 6 MHz on any one of 50 channels. Plug-in crystals and coils controlled the frequency. The 40-inch telescoping rod antenna slid into the case when not in use. American forces carried the SCR-536 across every theater of operations, from the beaches of Normandy to the jungles of the Pacific. Its compact size made it invaluable for squad-level communications where larger radios could not be employed. The British Wireless Set No. 38 served as the standard short-range man-pack radio for British infantry during the latter part of the war. Murphy Radio developed this high-frequency portable transceiver in 1941. The set proved a great success, with wartime production totaling 187,000 units manufactured. The set was a 5-valve design covering 7.4 to 9 MHz and was powered by a large dry cell battery carried in a separate haversack. The equipment carried by a soldier included a large aerial, a heavy battery pack, and a throat microphone. Range extended up to 4 miles, using a 12-foot rod antenna under ideal conditions, though actual performance varied considerably with terrain. An armored fighting vehicle variant was developed for use alongside the wireless Set No. 19 in tanks to allow direct communication between tank commanders and infantry. Although intended primarily for infantry patrols, the wireless Set No. 38 was also used by partisans to communicate with supplying submarines and even saw service linking Churchill and Sherman tanks to supporting infantry. The sets saw action at D-Day, Market Garden, and Operation Varsity, serving in all theaters where British forces fought. The German Tornister Funkgerät series represented the Wehrmacht's answer to portable infantry communications. The Torn.Fu.B1 was introduced in 1936 and became one of the first models of the new generation of military radio devices developed during Germany's rearmament in preparation for the war. Based on the Torn.Few.Day2 transceiver, this portable field set was intended for pack use, carried by two men with one handling the transmitter and receiver, while the other carried the battery pack, which also housed headphones, key, microphone, antenna gear, and other accessories. The set operated in the 3 to 5 MHz frequency range with 0.7 watt output for both amplitude modulation voice and continuous wave telegraphy. The vacuum tubes were the RV2 P800 type, and power came from one filament battery designated 2 CAM4 NC38 and two 90-volt anode batteries. The unit weighed approximately 45 pounds complete. A special device called the Fernbesprechungsgerät BF could be used for interfacing with FF33 field telephones, allowing telephone links to be established between two Torn.Few transceivers. The Torn.Few D2 operated in the 33.8 to 38 MHz VHF frequency range with 1.5 watt output. Range reached approximately 10 kilometers with continuous wave and 3 kilometers with voice. This common infantry set was used for voice radio nets and could be used on the move, with one man carrying the transmitter receiver and the other the battery power supply and handset, with a cable linking the two men together. This set was comparable in range, performance, and frequency band to the American SCR 300, though it used amplitude modulation rather than the superior frequency modulation of its American counterpart. The TFUG.K transceiver was introduced in 1943 and transmitted on the same frequency range as the Torn.Fu.F while receiving on the same range as the Torn.Fu.C. German infantry used these sets on every front from Poland in 1939 to the final defense of Berlin in 1945. The Soviet A7 VHF radio transceiver was developed during the war and used for communication in rifle brigades and regiments. The complete station was designed to be transported by an individual soldier as a portable manpack system. The A7 featured narrowband frequency modulation, making it one of the few Soviet radios to use this more advanced modulation technique. Setting the frequency of the receiver and transmitter circuits was adjusted in tandem by one control handle, simplifying operation under combat conditions. Frequency range covered 27 to 32 MHz across 101 channels. Transmitter output power reached 1 watt. Antennas included a whip with a height of 2.5 meters or a flexible wire 6.4 meters long. Range on rough terrain extended to 7 or 8 kilometers, in urban conditions to 3 or 4 kilometers, and on open terrain to 10 kilometers or more. The transceiver with power supplies and accessories was housed in a wooden box with shoulder straps for carrying as a backpack. Mass of the radio station was 15.5 kilograms while the battery weighed 6 kilograms. Deployment time was typically not more than 5 minutes. Time of continuous operation from one set was 35 to 40 hours. The A7A was a simplified version that reduced the total number of valves while decreasing energy consumption by about 30%. The A7B, introduced in 1945, increased the transmitting range by around 50%. Next on the list is tank and vehicle radios, the communication systems that enabled the coordination of armored warfare that defined the Second World War. The SCR 508 series was the standard American tank radio that equipped Sherman tanks and other armored vehicles throughout the war. The series was standardized on 22 July 1941 and used by armored forces for command and control of tank units. It replaced the earlier SCR 293 and SCR 245 and was used primarily in the M5 Stuart light tanks as well as the M4 Sherman medium tanks. The turret bustle of late series light and medium tanks was designed around this radio. The SCR 508 represented the Army's commitment to both frequency modulation and crystal tuning, providing the clearest voice communications available at the time. The system consisted of a BC 604 transmitter operating in the 20 to 27.9 MHz range with crystal-controlled 10 preset channels and output power of 25 watts. The BC 603 receiver was a superhet design with an intermediate frequency of 2.65 MHz, covering the same 20 to 27.9 MHz range with 10 programmable frequency presets. The power supply used 12-volt DC with dynamotor DM35A, or 24-volt DC with dynamotor DM37A for the transmitter, and 12-volt DC with dynamotor DM34, or 24-volt DC with dynamotor DM36 for the receiver. The complete radio set was used in tanks including M5 Stuart, M7 Priest, M10 Wolverine, M24 Chaffee, M4 Sherman, M36 Slugger, M4A3E2, M4A3E8 Sherman, M26 Pershing, and M46 Patton. The SCR 528 was exactly the same except with one less BC 603 receiver, and in most cases, the spot where the second receiver would have been was taken up by a CH-264 parts chest. This configuration was normally installed in the standard gun tanks of the platoon and company and weighed 181 pounds. The SCR-558 would only be installed when there was a shortage of the other models and weighed only 135 pounds. Command tanks had an additional SCR-506 mounted in the right front sponson, which could have 4 preset frequencies with a range from 2 to 4.5 megacycles transmitting and 2 to 6 megacycles receiving, allowing them to listen on the headquarters net while still talking to their own unit. Destruction of these radios would be top priority for the crew if they had to abandon a disabled tank. These radios saw service across North Africa, Italy, Northwest Europe, and the Pacific, providing American armored forces with a decisive communications advantage. The British wireless set number 19 was developed in 1940 by the War Office's Signals Experimental Establishment and by Pi Radio specifically for armored troops. First introduced in 1940, it began to replace the pre-war wireless set number 11. The Pi model was replaced with the Mark II model in 1941 and the Mark III model in 1942. Designed for use in tanks and armored vehicles, the radio provided 3 communication channels in one compact package. The A-set provided longer-range communications within the squadron or regiment operating in the 2 to 8 MHz frequency range, divided into 2 switchable subbands from 2 to 4.5 MHz and 4.5 to 8 MHz for medium to long-range communications. The B-set, or troop set, provided short-range communication between tanks in a troop using the 229 to 241 MHz VHF range, supporting 3 fixed crystal-controlled channels for frequency stability amid the vibrations and mobility of tank environments. The IC set provided internal communication between crew members inside the tank, incorporating an amplifier using a pair of 6v6 valves to distribute audio clearly amid engine noise. The Mark II complete weighed 86.25 pounds, with the sender receiver at 40.5 pounds, supply unit at 28.5 pounds, and carrier number 1 at 14.75 pounds. Modes included amplitude modulation voice, modulated continuous wave, and continuous wave. RF output for the A set ranged from 2.5 to 9 watts. Range for the A set reached 10 miles between moving vehicles, while the B set reached approximately 1,000 yards over unobstructed level ground, though practical ranges of 300 yards were more likely due to receiver insensitivity. The sets proved valuable for armored fighting in the Western Desert, where they enabled the coordination that made British tank operations effective. In 1942, the number 19 Mark II was produced in Canada by Northern Electric, Canadian Marconi, and RCA Victor, as well as by Zenith, RCA, and Philco in the United States. The British design was improved and interchangeability of components, including the valves, was instituted. A majority of Canadian sets used English and Cyrillic front panel lettering, the result of a Lend-Lease contract to the Soviet Red Army. With an additional RF amplifier, range increased up to 45 miles. During the Second Battle of El Alamein in October and November 1942, the A set high-frequency channels supported squadron-level coordination for the British 8th Army's armored thrusts, while its B set VHF capability enabled short-range, troop-level exchanges essential for navigating minefields and engaging Axis forces. The wireless set number 19 was in service with the Canadian Army from 1942 to about 1963. Major Rolfe was awarded the only Distinguished Service Order to come to the Royal Canadian Corps of Signals during the war for his actions coordinating communications during a critical engagement. The German Funkgerät 5 was the standard tank radio present in almost all German tanks and was the standard equipment for tank-to-tank communication within platoons and companies. This high-band HF and low-band VHF transceiver operated in the 27 to 33.3 MHz frequency range with a transmission power of 10 watts. The equipment provided for 125 radio channels at 50 kHz channel spacing. It was usually used with a 2-meter antenna mounted on the vehicle. Range was approximately 2 to 3 kilometers when using amplitude modulation voice and 3 to 4 kilometers when using continuous wave telegraphy. The FUG-5 plus FUG-2 radio configuration was the standard communication system for most German battle tanks, including the Panzer III, Panzer IV, Panther, and Tiger. This was a revolutionary amplitude modulation-based platform and was the first of its kind on the battlefield. The system not only incorporated complete radio telephone capabilities of both voice and continuous wave, but also boasted a sophisticated onboard intercom functionality fully integrated with the radio set. The Funkgerät 2 was a high-band HF and low-band VHF receiver that was never used on its own, but as an additional receiver in command tanks and section leader and company commander vehicles. It operated in the same 27 to 33.3 MHz frequency range, providing for 50 kHz channel steps for a total of 125 available channels. This allowed commanders to listen on one frequency while transmitting and receiving on another, meaning they could listen to the regimental command net while talking to subordinate units at the same time. The Funkgerät 6 was similar, but with 20 watts of output power for armored observation posts, which were usually early model tanks with some armament removed and replaced by equipment for artillery observers. Its greater range of approximately 4 to 6 kilometers for voice and 6 to 8 kilometers for telegraphy allowed observers to communicate effectively with armored unit leaders. This was comparable to the American SCR 508 tank radio, which covered a similar frequency range of 20 to 27.9 megahertz at 25 watts, and the SCR 608 artillery variant operating in the 27 to 38.9 megahertz band. The major difference between German Army tank sets and U.S. Army tank and artillery sets was the American use of frequency modulation for the high HF and low VHF bands. German armor relied on these systems to execute the combined arms tactics that made the Blitzkrieg so devastatingly effective in the early years of the war. The radio network allowed artillery and air support to be called down on stubborn enemy positions immediately with ground controllers, familiar with aircraft capabilities, coordinating pinpoint strikes when ground commanders needed them. Let us move on to aircraft radios, the communication and navigation systems that kept pilots connected to ground controllers and each other across the skies of the war. The SCR-274N command set was the standard American aircraft communication radio used throughout the war. The Type K command radio had been developed in 1936 and 37 as a modular communication system for aircraft use with separate receivers for separate wavebands, separate transmitters, control boxes, and accessories. It had been tested and improved for military use from 1939 onward. In 1940, the U.S. Navy started installing the equipment as RAY-T and RAV sets, while the U.S. Army Air Corps introduced the equipment as SCR-274N after May 1940. The N suffix signified a Navy design that the Army adopted. From these sets and their successors, approximately 1,450,000 units were produced. The command designation referred to the radio's function of communicating between aircraft, while the liaison function was to communicate back to base, though functions often became blurred in use. A fighter like the P-38 Lightning or P-51 Mustang would usually have one receiver and one transmitter fitted. A bomber like the B-17 Flying Fortress, the B-24 Liberator, or the B-29 Super Fortress would often have 3 receivers and 3 transmitters fitted. The receivers covered different frequency ranges, including the BC-453, covering 0.19 to 0.55 megacycles, the BC-946 covering 0.52 to 1.5 megacycles, the BC-44 covering 3 to 6 megacycles, and the BC-455 covering 6 to 9.1 megacycles. The receivers were remotely mounted and controlled with a BC-473 one-receiver control box, a BC-496 two-receiver control box, or a BC-453 receiver control box. According to the Airborne Radio Equipment Manual of the Signal Section Air Service Command, dated April 1943, the SCR-274N was used in bombers B-17, B-24, B-25, B-26, and A-20, fighters P-38, P-39, P-40, and P-51, and transport C-46 and C-47. The radios had amplitude modulation, voice communication, and 2 wave-modulated continuous wave Morse code capability. Despite the use of octal-based vacuum tubes, they were compact, rugged, and lightweight. Many became surplus after the war and were often converted for amateur radio use, and sets in original condition are now becoming rare. The German Funkgerät 10 series was the standard radio installation used on twin-engine and larger Luftwaffe aircraft. It was introduced around 1939 to replace the Fu-G3 installation. New bombers like the Junkers Ju-88 were designed to use the Fu-G10 from the outset. By September 1939, all long-distance Luftwaffe aircraft were equipped with Fu-G10 systems. The Fu-G10 panel contained 2 transmitters and 2 receivers. One pair operated in the medium frequency range from 300 to 600 kilohertz, while the other pair operated in the high frequency range from 3 to 6 megahertz. Most of the Fu-G10 series used a fixed-wire aerial between the fuselage and tail fin, or a retractable trailing aerial wire. Typical power was 70 watts. Up to the date of Germany's defeat, approximately 50,000 systems had been delivered, comprising a total of 300,000 individual units. The reliability and ruggedness of these radios made them favored by crews, where reliability was key in combat. Germany had no quartz of its own, so crystals had to be imported, which was against the orders of Hermann Göring, who had been given the task of making Germany self-supporting. As a result, quartz crystals were only used for frequency calibration, rather than for frequency control. Less than 1 million crystals were produced in Germany against 30 million in the USA alone from 1941 to 1945. The Fuji Tenzi-Was incorporated a fixed loop direction finding aerial and a homing device for navigation to a ground station, becoming standard equipment on most fighter aircraft from late 1943 onward. Japanese aircraft radio systems faced significant challenges throughout the war that limited their effectiveness compared to Allied systems. The Type 96 Q Mark II radio set was a Navy aircraft transceiver capable of voice and continuous wave communication with a frequency range of 300 to 500 kHz and 5,000 to 10,000 kHz. It was made by Nihon Musen Company, now known as JRC, in July 1941. The radio set was developed in 1936. Very early in the war, the lack of reliable radios severely limited tactical control options that could be exercised by Japanese flight commanders. Famed ace Saburo Sakai wrote of the death of fellow pilot Miyazaki Yoshio and the near ambush of Lieutenant Sasai Junichi under circumstances where formations had drawn apart, and he was unable to tell the straying aircraft that they were about to be bounced by enemy fighters. These incidents occurred over New Guinea in May 1942. Later, during the air battles around Guadalcanal, Japanese fighter formations had great difficulty coordinating escort actions due to heavy cloud conditions degrading visibility at multiple altitudes, as cited by historian John Lundstrom. A document titled Operational History of Japanese Naval Communications from December 1942 to August 1945, published by the Military History section of Headquarters Army Forces Far East as a translation of a document written by Japanese officers, noted problems encountered both in technology and in the attitudes of personnel that caused difficulties throughout the war. The radio sets were well designed and, at the beginning of the war, well built. As the war progressed, shortages of raw materials began to affect the quality of radio components. One of the earliest problems encountered was a lack of coordination between the manufacturers of the radios and the aircraft builders. The radio systems installed in the early A6M2 and A6M3 variants of the Zero were the Type 96 Q Model 1 voice and telegraph system and the Type 1 Q Model 3 radio direction finder, which operated in the low to medium frequency bands. These limitations meant Japanese pilots often relied on visual signals and predetermined attack patterns rather than the real-time coordination that Allied pilots enjoyed, placing them at an increasing tactical disadvantage as the war progressed. Continuing with naval and marine radios, the portable and shipboard systems that connected forces conducting amphibious operations across the Pacific and beyond. The TBY radio was used by the United States Marine Corps and Navy during the war as a portable transceiver for amphibious operations. This late 1930s design for the U.S. Navy was reportedly better than earlier Army gear of the same vintage. Operating over a frequency range of 28 to 80 megacycles with about a half-watt output, it provided short-range continuous wave and amplitude modulation voice signals across 4 bands covering 131 different channels. Between assault troops on the beach and a supporting destroyer, the transmit range would be a few thousand yards. In the jungle, range was much less. The TBY had been designed specifically for Naval and Marine Corps landing operations and operated in the VHF portion of the radio spectrum, so it could work efficiently with a short vertical antenna. It was a self-contained unit that could be worn as a backpack, transported and operated by one man instead of the 4 required for the larger TBX. The TBY weighed 33.7 pounds, including the battery. The first field use of the TBY radio was at Tarawa, where problems became apparent when water damaged the electronics during the contested landings. The case was made from sheet metal folded into shape, with many holes where water could enter its circuits. After-action reports from PT boat squadrons in the South Pacific indicate that TBY radios were used to good effect between boats when HF radio problems occurred. The TBY improved through the TBY 8 series with incremental changes to improve water resistance and antenna strength. The Navajo Code, talkers employed various radio systems including the TBY and TBX to transmit their unbreakable code across the Pacific battlefields. The Marine Corps' Navajo Code program was established in September 1942 following a recommendation by Philip Johnston to Major General Clayton B. Vogel, Commanding General of Amphibious Corps Pacific Fleet, whose headquarters was at Camp Elliott. Johnston was the son of a missionary who had spent much of his childhood on the Navajo reservation and was a World War I veteran who knew of the military's search for a code that would withstand all attempts to decipher it. He believed Navajo answered the military requirement because it is an unwritten language of extreme complexity. The first cadre of 29 code talkers, known as the First 29, designed and implemented the code with little formal cryptographic training. They devised a system built on word substitution, where common military terms were assigned a Navajo code word, and each letter of the alphabet was assigned at least one code word so other terms could be spelled out. Since there was no existing Navajo word for submarine, the code talkers agreed to use the term besh-lo, which translates to ironfish. The word for bomb was egg, and the names of different birds stood in for different types of aircraft. Code talkers could translate 3 lines of English in 20 seconds, instead of the 30 minutes it took to encode a message with existing cipher machines like the M209. The code talkers sent communications by telephone and radio in their native language. Most were assigned in pairs to a military unit, with one operating the portable radio, while the second relayed and received messages in the Navajo language and translated them into English. Their work was highly dangerous, especially in the Pacific, because Japanese soldiers would deliberately target officers, medics, and radiomen, and code talkers had to keep moving as they transmitted their messages. By the end of the war, roughly 400 Navajo men served as code talkers, and 13 had been killed in action. They participated in every assault the Marines conducted in the Pacific from 1942 to 1945, serving in all 6 Marine divisions, Marine Raider battalions, and Marine parachute units. At Iwo Jima, Major Howard Connor of the 5th Marine Division declared that were it not for the Navajos, the Marines would never have taken Iwo Jima. During the first 48 hours while landing and consolidating shore positions, he had 6 Navajo code talkers working around the clock. In that period alone, they sent and received over 800 messages without error. The Japanese Chief of Intelligence, Lieutenant General Seizo Arisue, said that while they were able to decipher the codes used by the U.S. Army and Air Corps, they never cracked the Navajo code. After incidents where Navajo code talkers were mistaken for ethnic Japanese and captured by other American soldiers, several were assigned a personal bodyguard whose principal duty was to protect them from their own side. Next on the list is strategic and command radio systems, the powerful installations that coordinated armies and transmitted intelligence across continents. The German Enigma machine stands as the most famous encryption device of the war, though it was not itself a radio, but rather a cipher machine used to encode messages before radio transmission. The Enigma has an electromechanical rotor mechanism that scrambles the 26 letters of the alphabet. In typical use, one person enters text on the keyboard and another writes down which of the 26 lights illuminates at each key press. Arthur Scherbius was a German engineer who patented the Enigma machine shortly after World War I, marketing it initially to banks, commercial firms, and diplomatic services. By the mid-1920s, German military officials recognized its potential for secure, decentralized communication. The German Navy introduced the machine in 1926, followed by the Army in 1928. The Wehrmacht's Enigma I was introduced in 1932 and quickly became the standard model for German armed forces throughout most of the war. It differed from commercial versions in wiring design and configuration options, which provided added layers of encryption. The action of pressing a key moved one or more rotors so that the next key press used a different electrical pathway, meaning a different substitution would occur even if the same plaintext letter were entered again. The number of possible settings reached approximately 159 quintillion combinations, making brute force decoding seem impossible. Pre-war German military planning emphasized fast mobile forces and tactics, later known as blitzkrieg, which depended on radio communication for command and coordination. Since adversaries would likely intercept radio signals, messages had to be protected with secure encipherment. Compact and easily portable, the Enigma filled that need. In December 1932, Polish mathematician Marian Rejewski at the Polish Cipher Bureau broke the code using mathematical permutation group theory combined with French-supplied intelligence material obtained from German spy Hans Thilo Schmidt. When Germany invaded Poland, the Poles turned their information over to the British, who set up a secret code-breaking operation at Bletchley Park. Alan Turing, a Cambridge University mathematician and logician, provided much of the original thinking that led to upgrading of the Polish cryptologic bomb. He developed the bomb, an electromechanical machine that helped deduce the daily Enigma settings. The prototype named Victory was installed at Bletchley Park in March 1940 and began deciphering Luftwaffe communications. By 1945, there were some 2,000 women of the Women's Royal Naval Service operating the bombs. On 1 February 1942, the Kriegsmarine began using the M4 model, a 4-rotor variant that significantly expanded the key space and temporarily halted Allied decoding efforts until the capture of cipher keys and use of much faster U.S. Navy bombs enabled regular rapid reading of U-boat messages to resume. The intelligence codenamed Ultra is credited with shortening the war substantially and may even have altered its outcome. High-powered mobile radio sets became common at division and regimental level throughout all armies during the war. In communications electronics, the Second World War was, in one sense, similar to the First World War. in that the most extravagant pre-war estimates of military requirements soon proved to represent only a fraction of the actual demand. The need for all kinds of communication equipment and for improved quality and quantity of communications pyramided beyond the immediate capabilities of industry. An increase in manufacturing plant became vital, and research and development in the communications electronics field was unprecedented. The early German blitzkrieg with tank and armored formations placed a new order of importance on reliable radio communication. The development of the air, infantry, artillery, and armored team created new requirements for split-second communication by radio among all members. Portable radio sets were provided as far down in the military echelons as the platoon. During the Great Patriotic War, Soviet ground forces were supplied with radio stations, including the 12RT, RBM, A7, RSBF, RAF, KV3, and others, along with many samples of telegraph and telephone equipment, including field telegraph devices, tube DA-43. At the end of 1944, Soviet signal troops began to receive the radio station RAF KV-4 with carbide equipment, which ensured the operation of a direct printing telegraph devices over radio lines with protection against interference. The industry of the Soviet Union mastered the production of ultra-short wave radio stations, and the saturation with radio communications equipment was constantly increasing at various command and control levels. Multi-conductor cables provided wire communications that could be reeled out rapidly, and as many as 4 conversations could take place on them simultaneously through the use of carrier telephony. The Germans were the first to use this type of military long-range cable, and their example was followed promptly by both the British and United States forces. With high-powered mobile sets, telegraph communication could be conducted at distances of more than 100 miles with vehicles in normal motion on the road. Major telephone switchboards of much greater capacity were needed and developed to satisfy the greatly increased number of telephone channels required to coordinate the movements of field units whose mobility had been expanded many times. Let us move on to direction finding and navigation systems, the specialized radio equipment that guided aircraft and ships through hostile skies and seas. The German Pilaret 6 was a long and medium-range direction finding set and homing device used mainly on bombers. Codenamed Alex Sniakowski, it was manufactured by Telefunken and fitted to aircraft, including the Arado R-234, Dornier Do 217, Junkers Ju 87, Junkers Ju 88A4, and later variants, Junkers Ju 188, Junkers Ju 290, Junkers Ju 388, the Heinkel He-177A heavy bomber, which was Germany's only heavy bomber design and service, and both the Heinkel He-219A and Junkers Ju 88G night fighter series. Frequency range was 150 to 1200 kilohertz. A flat equivalent of a direction finding loop was used to reduce drag over a protruding antenna, made up of a series of metal strips in a sunburst pattern often fitted under a round flush-fitting plexiglass. Cover. A small whip aerial was also fitted to the Fuji-10 radio mast. Version Pilgarat 5 was of similar performance, but used a manually controlled loop antenna with control via an electric servo motor. The Luftwaffe operationally deployed 3 beam navigation systems during the first part of the war called Knickebein, X-Gerat, and Y-Gerat. Development of Knickebein began in the late 1930s based on the Lorentz blind landing system. The initial work was to develop their instrument landing system, but further work investigated how far a beam of that frequency could be used to guide an aircraft to its target. German bombers used these navigation beams during the Blitz against Britain until British scientists developed countermeasures that bent or jammed the beams, causing bombs to fall harmlessly in fields rather than on their intended targets. The Battle of the Beams became a critical electronic warfare struggle that influenced the entire air war over Britain. A new long-range electronic navigation device, known as LORAN, was developed by the Allies for use by both naval vessels and aircraft. Short-range navigational systems called SHORAN were also developed for more precise positioning. Combinations of radar and communications for the landing of aircraft in zero visibility were perfected, including the Ground-Controlled Approach System, or GCA. Combinations of radio direction finding, radar, and communication systems were developed and used for ground control of intercept aircraft in the system called GCI for Ground-Controlled Intercept. Radio-controlled guidance of falling bombs enabled an operator in a bomber to direct a bomb to the target with far greater accuracy than unguided munitions. Electronic countermeasures made their appearance in the form of jamming transmitters to disrupt radio channels and radar, navigation, and other military electronics. These systems fundamentally changed the nature of air and naval warfare, allowing operations in weather conditions and at night that would previously have been impossible. The military services learned well from their wartime experiences the importance of scientific research and development in communications electronics, laying the groundwork for the electronic battlefield that would characterize conflicts for decades afterward. Finally, we have specialized field radios developed for specific tactical requirements and unusual operational environments. The Japanese Type 94 series represented the standard field radio equipment for the Imperial Japanese Army throughout the war. The Type 94 Mark IIIA transceiver was introduced in 1934. The designation derived from the Japanese calendar year and was used by division and regiment stations in the field. The one-tube transmitter was continuous wave, only using a Hartley oscillator, with a frequency range of 400 kHz to 5.7 MHz. The RF output was 15 watts, with a range of about 80 kilometers. Power came from a hand-cranked generator. The 5-tube super heterodyne receiver had a frequency range of 350 kHz to 6 MHz. Communication range for telephonic communication was 50 kilometers, and for telegraphy, 80 kilometers. The antenna was an opposite L-type, with pillar height of 7 meters. The Type 94 Mark VI was a miniature single-valve, portable transceiver intended for infantry short-range communication up to 2 kilometers. The radio was extremely small for the era and suitable for voice and Morse transmissions in the VHF band from 25 to 45.5 megahertz. At Guadalcanal, American Marines captured a number of these radios and immediately put them to use for their own communication. The radios worked well, but were only suitable for short-range communication. Immediately after the war, the U.S. ordered the destruction of all German and Japanese wartime equipment, which is why so few of these radios have survived. The German Feldfunksprecher series provided frontline infantry with compact VHF communications. The Feldfunk B operated in the 90 to 110 MHz range with 0.15 watt output for amplitude modulation voice and continuous wave, with a range of 1.5 kilometers. It was used by infantry in the first half of the war, and thereafter by motorcycle troops. The Feldfunk B1 was used by pioneers, while a simplified version called B2 was used by Panzer Grenadiers. The Feldfunk C operated in the 130 to 160 MHz range for infantry use. The Feldfunk F operated in 28 to 33 MHz and could interwork with the FU-G5 of armored units, providing crucial communication between Panzer Grenadier infantry and supporting tanks. The Feldfunk H covered 23.1 to 28 MHz for assault guns and Sturmartillerie units. Lorenz was one of the bigger factories involved in making the Tornister and Feldfunk series for the Wehrmacht from 1939 to 42. Later production was taken over by Saba, while Lorenz concentrated on larger transmitters together with Telefunken and Philips. In 1942, Saba started making complete radio units like the Feldfunk B1, B, and C Tornister Gerät. These compact radios allowed German forces to coordinate infantry and armor in the integrated tactical operations that proved so effective in the early campaigns of the war. Radio communications transformed warfare during the Second World War in ways that reshaped military doctrine permanently. The ability to coordinate airstrikes with ground advances, to direct naval gunfire from forward observers, and to warn fighter pilots of approaching enemy aircraft created opportunities for combined arms operations that previous generations of commanders could only have imagined. American frequency modulation technology provided clearer voice communications that proved especially valuable in the noise and chaos of tank warfare, giving Allied armored forces a real advantage in coordination. British innovation in signals intelligence at Bletchley Park turned intercepted radio messages into a decisive strategic advantage that shortened the conflict. German engineering produced reliable systems that enabled the coordination of blitzkrieg tactics, though reliance on amplitude modulation left their communications more vulnerable to interference than American FM sets. Japanese radio systems initially performed well but suffered from production quality issues as the war progressed and raw materials became scarce. Soviet designs emphasized ruggedness and simplicity suited to their harsh operational environments. The human element proved as important as the technology itself. Navajo code talkers demonstrated that an unwritten indigenous language could provide security that no cipher machine could match, transmitting hundreds of error-free messages under fire on the bloodiest battlefields of the Pacific. Radio operators in every army learned to function under direct enemy fire, maintaining communications even as their positions came under attack. The race between code makers and code breakers accelerated the development of electronic computing, with machines like the Bomb and Colossus laying foundations for the digital age. Many of the veterans who maintained and operated these systems went on to careers in the post-war electronics industry, applying wartime experience to civilian applications. The compact handheld transceivers that soldiers carried at Normandy and Iwo Jima evolved into the mobile communications technology that would eventually connect the world. Every radio system covered in this video played its role in the greatest conflict in human history, and their legacy continues to influence military and civilian communications technology long after the guns fell silent in 1945.